Hello, my dear physicists. Today we are going to be discussing a problem in fluid mechanics, and we are talking about pressure intensity inside a water droplet. So here the instructions are saying show all working, give answers to 3 significant figures unless otherwise stated. So the scenario goes, on a quiet afternoon, Miriam, an A-level student of physics, sits by the school laboratory window watching fine mist settle on the glass. Curious about the tiny spherical beads of water clinging to the pane, she decides to investigate the effect of surface tension on the pressure inside the droplet. Miriam measures one nearly perfect spherical droplet and finds its radius to be R is equal to 1.50 millimeters. She uses the standard value for the surface tension of water at room temperature, and this is sigma is equal to 0.72 Newton per meter. As she works, two neighboring droplets, one with radius R1 is equal to 1.50 millimeters, and the other R2 is equal to 3.00 millimeters, slowly merge into a single larger droplet. Miriam records data and asks you to help answer the following questions so she can write up her lab report. So, question 1. Derive an expression for the excess pressure inside a spherical droplet due to surface tension. Next, calculate the excess pressure inside the droplet with radius 1.5 millimeter relative to the outside pressure. After the two droplets with radius R1 equal to 1.5 millimeter, the other R2 equal to 3.00 millimeter, coalesce. So when they coalesce, they form a single spherical droplet. Determine the radius of the new droplet. Assume volume is conserved. This is the assumption they have given us to take. Number 4, calculate the excess pressure inside the new droplet and compare it with the excess pressure that was inside the smaller droplet R1 before coalescence. Comment on the difference. Next is that briefly explain how the radius of a droplet affects the internal excess pressure. Ladies and gentlemen, let's see how we can answer these questions asked to us. So we're going to say, first of all, solution. So among the things that we need to jot down, we are going to first say, let P be the pressure inside the droplet above the outside pressure. So we are saying a change in pressure should equal to P minus 0. Here we are saying this is going to be P and is going to be P above the outside pressure. So in other words, this is actually going to be gauge pressure because it is above atmospheric pressure. Yeah, the outside pressure for this droplet is actually atmospheric. So any pressure above it and is called P, this is going to be the gauge pressure. Okay, next is we are going to also let D be the diameter of the droplet. Diameter of the droplet. And then we are also going to be using this sigma to be the surface tension of the fluid, stroke liquid. So since here we are dealing with water droplet, then the fluid involved is going to be liquid water. So let's consider these diagrams. This is a droplet that we are talking about, and we are considering a perfect spherical, okay, near perfect spherical water droplet, because that's what Miriam actually used in her experiment. Then when we split it into two, we realize that there is pressure inside. So this pressure inside is always going to work in order to break down the droplet. So it is acting against the walls of the droplet inside. Whereas surface tension is actually the force that acts per unit length on the surface. So you can see this is going to be acting on the surface always in a way that it tries to make sure that the surface of the liquid is stretched and behaves as if it is a stretched membrane. So if you get your skin and stretch it apart and then place something on top, you'll find that that particular object is going to float. So likewise, the way you're stretching that skin is the same way surface tension works to stretch the surface of this droplet. So when we do the cross-sectional area and observe it critically, we realize this is how the surface tension is going to be working, and also the atmospheric pressure is going to be working against it. This is the atmospheric pressure acting against it, but also the pressure inside, remember, is now the one that is going to be opposing this. Now, again, when we furthermore split this droplet, we realize in two dimensions, this is how the surface tension is going to be working, and this is how the pressure intensity is going to be, and then its geometry, we are talking about the diameter of this droplet. So we have to determine the pressure and surface tension at equilibrium. But we shall begin with case 1, where we talk about force due to surface tension. So the force due to surface tension, we said that the surface tension is a force per unit length. So that means if we want that force, we would get the length on which that force is acting. When we multiply the two, we should be able to get the force. So since it is acting around the circumference of this circle, okay, then that means we shall say the force due to surface tension will equal to surface tension itself times the length, and then length here that we are talking about is the circumference. So we know circumference is the distance around the figure, like perimeter, but in circles we talk about circumference. Therefore, this is going to be pi d or 2 pi r. So let's maintain pi d for simplicity, and therefore this force due to surface tension will equal to sigma times pi d. So we can call that equation 1, and then we talk about case 2, the force due to pressure. Due to pressure inside the bubble. Okay, the water droplet. Inside the droplet. So this is going to be, again, we are talking about a circular object, and therefore this is going to be the pressure P times area. But area is equal to pi d squared out of 4. So what does that mean? The force will therefore equal to pressure times pi d squared out of 4. And you can call this equation 2. Therefore, Therefore, at equilibrium, because that's where we analyze these forces, at equilibrium, the two forces are equal. The force due to internal pressure and surface tension are equal. So from equation 1 and equation 2, therefore sigma times pi d will therefore equal to P times pi d squared out of 4. What does that mean? I just cancel out what is similar, or I just divide by pi d squared out of 4, pi d squared out of 4. Because I want pressure, so this and that will cancel. This d will, this 2 will cancel with this d here. The pi will go, the 4 will go upwards, and therefore P will equal to sigma times 4 divided by d, and this is equal to 4 sigma out of d. So if we bring in a radius, then we know that D is equal to R. So meaning that pressure will equal to 4 sigma divided by 2R. Okay, so by 2 here, 1 by 2, 2, and this becomes 2 sigma divided by R. So given sigma, which is the surface tension, and radius of the sphere, okay, which is the droplet, then we can determine the pressure intensity, which is the pressure value above the atmospheric pressure, which is outside the water droplet. So therefore, P will always be 2 sigma out of R. So let's look at the questions. Now we are told to calculate the excess pressure when the R is 1.5. So part B, with R equal to 1.5 millimeters, we have to change it to standard units. So R will be 1.5 times 10 to the power negative 3 meters. Just divide this by 1,000 and then you will get it in meters. So the pressure, therefore, I think also we need to determine the sigma, which is 0.072 Newton per meter. So we get our pressure. The pressure is going to be 0.072. We multiply by 2. We divide by 1.5 times 10 power negative 3. So from my calculator, this gives us 96.0 pascals, or 96.0 Newton per square meter, because 1 pascal is equal to 1 Newton per square meter. So that is also done. We go to part C. Part C required that, this is 3, part C required that after the two droplets with radius this and the other one that coalesce, they form a single spherical droplet. So we are to determine the radius of the new droplet, assuming that volume is conserved. So here the volume that we're talking about is the volume of air inside. Okay, volume of air inside the droplets. So we know that volume is conserved. So meaning the total volume of the new droplet will equal to the sum of volumes of the individual droplets. So that means, since the droplet in its geometry, it's a sphere, we know that volume of a sphere is equal to 4 out of 3 pi r cubed. So that means we are going to apply that. And if we assume that the new radius is r, and then these others are r1 and r2, then we are going to do it like this. let the new radius be r, and the others are r1 and r2. Therefore, from the conservation of volume, 4 out of 3 pi r cubed will equal to 4 out of 3 pi r1 cubed plus 4 out of 3 pi r2 cubed. Now, we just factorize out, so we'll have 4 out of 3 pi r cubed will equal to 4 pi out of 3 into r1 cubed plus r2 cubed. So we can cancel this and that, and we'll remain with r equivalent to the cube root of r1 cubed plus r2 cubed. So we just have to substitute in our values. So r will be the cube root of 3 into, we had 1.5 times 10 power negative 3. So we cube that, plus the other radius was 3.0 times 10 power negative 3. We cube that also, and then finally take the cube root of this value. So from my calculator, I find that r is 3.120 millimeters. So this is 3.12 times 10 power negative 3 meters. So the next question was to use this r to determine the pressure. So calculate the excess pressure inside the new droplet. Compare it with the excess pressure that was inside the smaller droplet before coalescence. Then comment on the difference. So for that matter, therefore, I will just come and say the pressure is going to be, this is 4 sigma out of D, or 2 sigma out of R. So we know this value. So this is going to be 2 times 0.072 divided by 3.12 times 10 power negative 3. So P, maybe we call it P new, becomes 46.15 pascals. Now, let's look at the pressure. We know P1 was actually 96.0 pascals. So let's look at P2, which is now going to be 2 sigma divided by R, but the R that we are going to use is 3. So this is going to be 2 times 0.702 divided by 3.0 times 10 power negative 3. My calculator gives me 48.0 pascals. So the comment, we see that the new droplets pressure, the new droplets excess pressure is slightly less than that of the 3.0 millimeter droplet, and much less than that of the 1.5 millimeter droplet. So because the excess pressure P, or just this P, is inversely proportional to radius, you will find that small droplets are going to have much larger excess pressure compared to the ones with large radii. So that's very important for us to comment. And finally, that is actually what was required of us. Explain how the radius of the droplet affects the internal pressure. First of all, here we realize that with the as radius increased, then the excess pressure also reduced. So here, in explanation, we just have to say that according to this formula, we realize that P is equal to 2 times sigma divided by R. So if we keep sigma or surface tension a constant, then that means we have to vary R. So you realize that as R increases, P reduces, and therefore P is inversely proportional to R, making radii of small diameter have excess internal pressure, and those with a larger radius giving us small pressure. So that is exactly what we have talked about. So the excess pressure is inversely proportional to the radius. Small droplets have much larger internal pressure relative to outside air. As radius increases, the excess pressure will always reduce. So ladies and gentlemen, this is the problem and its solution. Remember to subscribe, share, and like.